Hello, everyone. Welcome to week 7 of our course. I would like to congratulate all of you for doing a great job during prelims. So it's time to pat yourself on the back and say, "Good job, self. You're working very hard, so you deserve a treat." So I hope last week you enjoyed our study break because we celebrated our family days for the whole week. And now, for this week 7, we are now back into business. So let us discuss our first module for midterms. And I hope some of you had already read what our module is all about. Okay, so prior to watching this lecture recording, I also want you to read your module in advance. Okay, so let us start learning what our topic would be. So allow me to share with you my screen. So here we are now. Week 7 discussion, and it is all about rotation of rigid bodies. Okay, so yeah, my screen is already there. All right, so rotation of rigid bodies. I prepared these slides for you guys, and my sources are here listed. So credits to the sources of my lesson for this session. Okay, so first and foremost, let us define our terms. Okay, so what is rotational kinematics? Okay, so this describes rotational motion. And what is rigid body? Okay, we always say rigid body in physics. What does this mean? Okay, so a rigid body is actually an idealized model of a body which is a perfectly definite and unchanging shape and size. So all the points of a rigid body are fixed. So say for example, we have this DVD, what do you call this? Disc. Okay, we have this disc. So say for example, okay, so we have this disc. This is a rigid body because if you will put force into it, you cannot deform it easily unless you crack the disc. That's the time that it will be deformed. Okay, so for a rigid body, all the points there, the point here, the point here, the point here, are fixed. They are in its fixed axis or its fixed location. Okay, so when a rigid body rotates at a certain axis, so in this case, it rotates along its center of rotation here at the center of the disk, all the points will rotate also. Okay, so with that, with all the points, there is a displacement. Okay, so we will be learning about that later, what that displacement is. So if it, just to give you a preview, that displacement will be represented as the angle theta. All right. So more about rigid bodies, it is one where all the particles maintain their relative position. So as the body rotates, each particle moves and the relative positions do not change. So say for example, in the earth, okay, you have your globe here. The cities on the earth are always moving, but they do not get closer together. Okay, so say for example, Sydney in Australia is here, Bowling Green is at the northern part. So no matter how many rotations the earth does, those cities are fixed on their position. So that is what a rigid body is all about. Okay, so let's have our angular definitions. So we already defined earlier the change in the position of a rigid body, which is what we call as the angular position theta. So in rigid bodies or angular motion, we have to take note of the inertial frame, the point origin O, all right, and the angular position. Okay, and since we are moving, the point is moving from one position to another or one location to another, there is also the angular displacement. And the angular displacement is the difference between the two positions. So we have delta theta, which is the angular displacement, that is equal to theta 2 minus theta 1. So in our, if we may recall, in our horizontal motion, we have the displacement x, which is delta x is equal to uh, x2 minus x1. And for vertical motion, we have delta y is equal to y2 minus y1. Okay, so all of that are all during the interval delta t is equal to t2 minus t1. And we are having our angular position to be in radians, okay, because it is now an angle. We do not use in our computations the degrees, but we are going to use the radians. So we already know from trigonometry that one revolution is equal to 2 pi radians, and that is equal to 360 degrees. That is for one revolution. Okay, and of course, if we have 180 degrees, that would be equal to pi radians. All right, so this is it. We have our illustration here. We have our fixed point, and that is the point of rotation, and we have our radius r, and say for example our point is here. Okay, so when the point moves from this point to this point, okay, so that is equal to 1 rad. So our s is equal to our radius. Okay, what is this s here? Okay, this s is called as the arc length. Okay, so arc length is this one. Okay, the length where the point um is covering, okay, along its angular motion. Okay, so our arc length is actually equal to r times theta, because here we have 1 rad, that's why they are equal. But here our theta is not equal to 1 rad, so our arc length is equal to r times theta. So just simply multiply the radius times the angle in radians, and you get the length, you get the arc length, the the distance that our point is covering when it travels from theta 1 to theta 2. All right, theta, theta, sorry. Okay, so from our kinematics lesson, we can derive our kinematics equations also for our angular motion. Okay, so we just have to change our our symbols for that one. So we, instead of using x, we use theta for the displacement. Instead of using v for the velocity, we use omega. Is this omega? Okay, just counter check that. Okay, for angular velocity. And instead of using acceleration, we use alpha for angular acceleration. And we can now derive our four equations for rotational motion in terms of theta, omega, and alpha. Okay, so we already discussed that in module 2, the four kinematics equations. So just change the symbols there. For x, it becomes theta. For velocity, it becomes angular velocity. Omega, for acceleration, it becomes the angular acceleration alpha. So deriving the formulas, we can get for angular velocity to be equivalent to the change in the position, change in angular displacement per unit change of time. So delta theta over delta t. So we can also get the limit for that. Okay, in your calculus, you have this application for your study in your calculus. Okay, so we have to get reminded of the right hand rule. For the right hand rule, our fingers will represent the direction of rotation and our thumb will represent the direction of our angular velocity. So say for example, we have this disc rotating in this direction. Just look at the arrow. So our fingers rather, you curl our fingers in the direction of the rotation and our thumb is pointing upward. So that means the angular velocity is going up. All right. Now, if we go in opposite direction of our motion for our disc, just take a look at the arrow here. Okay. So we curl our fingers again. So our fingers is going in this direction. Okay. Can you see it? All right, like that. Okay. So our thumb is pointing downward, so our angular velocity is going downwards. All right. So you better practice. Just take note the four fingers represent akong tanawong lileon kung makita ba ang finger, the four fingers represent the direction of motion while the thumb represents the direction of the angular velocity. Okay, so you may practice that for yourself. Now, the average angular acceleration is equal to the change in the angular velocity per unit time. So you also have the limit. Now, acceleration is the second derivative of the change in position. So you have this as the second derivative. I know you know how to do this already in your calculus. All right. So just for the case of linear motion, the object will be speeding up if the angular acceleration is in the same direction of the angular velocity. But it will slow down if the angular acceleration is in opposite direction with the angular velocity. Okay, so say for example, here our disc is turning in this direction. So our thumb curls, no, our fingers curl in that direction and the thumb is going up, so our angular velocity is going upwards. Now, perhaps the angular acceleration is also going upwards, so that means our our object is speeding up. Okay, while if our angular acceleration is acting opposite to our angular velocity, that means that our object is already slowing down. All right, so we have this graph. Okay, so say for example, we have a graph of the time versus our acceleration and our angular velocity. Angular acceleration and angular velocity. So the angular velocity shows this green curve, while the angular acceleration shows this orange. Is that orange or yellow? Okay, orange line. Okay, now we are asked, okay, during which time intervals is the rotation speeding up, and during which time intervals is the rotation slowing down. So as what we had discussed earlier, it will speed up if the angular acceleration is in the same direction with the angular velocity, and it will slow down if the angular acceleration is in different direction with the angular velocity. Okay, so say for example here, okay, our angular velocity is in this curve and our angular acceleration is this straight line. So you are asked when, okay, what time will the object will be speeding up and what time will our object be slowing down. Okay, so you answer that as your activity in your module. Okay, so I have the answers there. So um just figure that out by yourself, okay, later, because it appears also in your module. All right, so I hope earlier you already derive the formulas for our angular motion from the kinematics equations. So they are here already. I will present them to you. So from kinematics equation 1, instead of using velocity, we use now angular velocity. And instead of using acceleration, we use now angular acceleration. Okay, so you are very familiar of these equations already. And instead of using x, we are now using theta for angular displacement. So this is our comparison between the linear motion and our angular motion. Okay, so these are our kinematics equations for linear motion again and for angular motion. So they are just the same. And you have here sample problems. These also appear in your module. So practice answering these problems. Now let us proceed to rotational versus linear kinematics. We already learned earlier that the arc length is equal to r times theta, where r is the radius and theta is the angle of displacement in radians. Never forget that. Now, we can also get our linear velocity, and the linear velocity is equal to r times the angular velocity. Okay, sometimes we are asked for the linear speed, so we are just going to use this formula. V is equal to r omega. And we can also get the tangential acceleration as well as the radial acceleration. So when we say tangential acceleration, that is our acceleration is not acting directly along the x-axis and along the y-axis, okay? But it is only tangent to our motion, which is our circular motion for this time, right? Okay, so our acceleration is this. So we have to get the x and y components of the acceleration again. So we already discussed vectors in module 1, so never forget how to get the x and y components of our vectors. So here, our x and y components for our acceleration would be the tangential acceleration and the radial acceleration. And the formulas are now here derived for you guys. The tangential acceleration is equal to r times the angular acceleration, and the radial acceleration is equal to the angular velocity squared times r. So just remember these formulas. And you can now solve problems when you are asked for the tangential and for radial acceleration. Okay, so as what I've said earlier, we use radians and not the degrees. Okay, so if you are given angles to be in degrees, kindly convert that into radians first. And how to convert degrees to radians? We just use 180 degrees is equal to pi. Okay, so here in this case, we have 60 degrees. So how are we going to convert that into radians? Okay, 60 times pi over 180, and you get pi over 3 rad. That's just it. So practice that, but I know you have that in your trigonometry. Okay, so we have this in your module. So kindly answer this one. I'm gonna give you this as your um I'm gonna give you this as a sample problem. Okay, so kindly take a screenshot or take a photo, and I will be sharing to you my notes for this one. Okay, I will stop sharing this, and I will go to my notes. Okay, I hope you guys are bearing with me. Start broadcast. Okay. So am I there already? All right, it's there. Okay, so we are having here Anong dili man siya na code? Okay, there. We have a car that has a tires with radius 20 centimeters. Okay, so we have our given radius 20 centimeters, and converting that into meters, we have 0.200 meters. It begins to accelerate forward. The acceleration comes from the engine, which produces an angular acceleration of the tires to be 12.0 rad per second squared. You are asked for the tangential acceleration of the tires. So you are asked for the tangential acceleration of the tires given r and given the angular acceleration. So let us go back to what our formula for tangential acceleration. Our tangential acceleration is just equal to r times alpha. So what we can do here is just to multiply our given, which is the radius zero point 0.2 meters times our angular acceleration, 12 radians per second squared. So our tangential acceleration, kindly get your calculator. Please be proactive in this course. Our tangential acceleration is 2.40 meter per second squared. Okay, kindly take note of the number of significant figures. It must have three significant figures since our given values are in three significant figures. All right, so moving on, I will now share my screen here again. Okay, is it there already? I will check. Kay basig wala na po ko. Just like, okay, it's there. All right, so moving on, we have also rotational inertia. And we also call this as the moment of inertia. So when we say rotational inertia, it is the measure of the resistance of the object to change in its rotational motion. Okay, so it will resist the change in rotational motion. There are objects that are hard to rotate. Okay, and that is the moment of inertia. Okay, say for example, I have this water bottle. Okay, and when I open my water bottle, okay, sometimes it's hard to rotate this water bottle, okay, because of the moment of inertia of the disc, the cap of the water bottle. Okay, so another example would be if I'm going to have my water bottle this way, okay, and I hold it here at the center, okay, and I want to rotate my water bottle like that. Okay, so will I be able to rotate the water bottle easily? Okay, there is that moment of inertia or rotational inertia, which is the resistance of the object to change in its rotational motion. So our formula for that is equal to m1 r1 squared plus m2 r2 squared and so on, where m1 is the mass of object 1, okay, r1 is the radius or the distance of the mass from the pivot point. What is pivot point? Pivot point is the point of rotation or the axis of rotation. Okay, so the moment of inertia is in kilogram meter per second squared. Okay, that is the unit for the moment of inertia. All right, so in your module is very long, appears to be very long, and your module appears to be intimidating. But do not get intimidated with the formulas, with the all the letters there in the formulas, okay? But this is just very easy. Let's just be reminded of M1 R1 squared. Okay, so I have to turn on okay, I have to charge my laptop. Okay, so let's have this example. This is a very easy example. This simplifies the examples that are there in your module. Okay, so we are going to discuss this example so that you can understand your module properly. So kindly take a screenshot or a photo of a problem so that when I share my lecture notes, you can glance at the problem. Okay, so already done. I'll share my lecture notes again. Okay, I hope you guys are following. Okay, it's there. Okay, so our problem, let's do another page for that. You have 4-point masses that are 3 kilograms each and are arranged in a square on massless rods. The length of a side of a square is 0.5 meter. You are asked for the rotational inertia for rotation about an axis. We are asked for 3 axes. Okay, first axis, if it is passing through masses B and C, second axis, if it is passing through masses A and C, and the third axis is passing through the center of a square. So let us first have our illustration for this. Okay, so we are given 4-point masses. Okay, so let's just draw our 4-point masses this way. 3 and 4. This is mass A, this is mass B, this is C, and this is D. Now, each of the masses is 3 kilograms, so they have the same mass. Okay, they are arranged in a square on massless rod. So they are attached in massless rods. Okay, so therefore, we do not account for the mass of the rod. Okay, so the length of a side of a square is 0.5 meter. Okay, so since this is a square, all the sides have equal length. So all the sides have 0.5 meters in length. Now you are asked for the rotational inertia for rotation about an axis passing through masses B and C. So where is that? I will use another color for that rotation. We are asked for this one. Okay, for letter A. All right? So we say that we are rotating our object in that direction. Okay, so say for example, I have this calculator. Can you see my calculator? Wait, so I can see myself. Okay, I have this calculator. Say for example, this is square. All right, because this is rectangular. Okay, so this is point point A, point B, point C, and point D. All right. So again, this is point A, B, C, and D. Okay. So since this is point B and this is point C, I am rotating in this way, like that. So what are the points rotating in that axis of rotation? Points A and D are rotating around it. Is that understood? Okay, so for that one, it is A. I will use another color for that. It is A that rotates around that point, and it is D also that rotates around that point. Okay, so there are two masses rotating along that axis BC, which are points A and D. Okay, so getting our moment of inertia, we have our formula m1r1 squared plus m2r2 squared. Okay, so our masses are given, they are all 3 kilograms each. 3 kilograms for n1 times the radius. Okay, this time, what would be the distance from point A to our axis of rotation? Okay, so we are going to solve for this distance here. That would be our R. Okay, and we can solve that through our Pythagorean formula. Okay, so don't forget your Pythagorean formula. All right, so solving for our hypotenuse. Okay, so why is that so? Okay, so we have, let us cut our square into a right triangle. Okay, so this is our 0.5 meter, and in that side 0.5 meter, and we are going to get the hypotenuse. In getting the hypotenuse, this is just equal to the square root of 0.5 squared plus 0.5 squared. So kindly never forget your formulas from your prior knowledge. Okay, so our hypotenuse is 0.707106781. Kindly get your calculator, okay? And do not round off your answers first, okay? Just round off at the last part of your solutions. All right. So since we get now our hypotenuse, this is our hypotenuse. Since that is this whole thing here, and we are only asked for the R, the radius, so half of the hypotenuse. So let's just divide that by 2. Okay, so dividing our hypotenuse by 2, we get 0.3535539. 35355. Okay, that one. So kindly counter check with your calculator. So that is in meter. Plus the same 3 times, I will just shorten this one. Okay, not including the units and rounding this off, but do not round off again. All right. And our moment of inertia for letter A along axis BC is equal to 0.75 kilogram per meter squared. So this is our answer for letter A. Now, let's proceed to letter B. For letter B, so gani ask sa letter B, passing through masses A and C. Okay, so let us draw again our square. So this is A, B, C, and D, and they are in masses rods. You are asked to pass through A and C. So our axis of rotation, it will be in red, will be here. Okay, so what are the masses that will be rotating around A and C? So let us go back to our calculator. Makitaan? Okay, let us go back to our calculator. Again, this is A, B, C, and D. So we are now rotating A and C along A and C. So this is our axis of rotation. Dila na po magtuyok-tuyok. Alright. So B and D are rotating along A and C. Do you get it? For A, this will be our axis of rotation. So paganon siya. Now, this will be our axis of rotation. So, paganon siya. Okay, so I hope you get that one. So, B is rotating along that one, and D is rotating along that axis. All right. So, our moment of inertia this time would be the same formula, m1r1 squared. You have free, I will not include the units anymore. And you have 0.5 squared, that is for mass B. And for mass D, still 3 times 0.5. squared. So our unit of inertia, a moment of inertia rather, is 1.5 kilogram meter squared. So kindly counter check that one. And let us proceed to C. For letter C, this time, you are passing through the center of the square and perpendicular to the plane of the square. So you have our square again. Let us draw again our square A, B, C, and D. Now, where are we rotating? Our pivot point is at the center, according to our problem. So let's get our calculator again. Point A, B, C, and D, and we are rotating at the center. So, paana na ang atong rotation? Alright? So, is that clear? For A, this one, diagonal rotation, diagonal axis of rotation. For B, at the side, axis of rotation, like this. And lastly, for C, axis of rotation is at the center, so like this. Okay, so how many points that we rotate around that axis of rotation? We are rotating all the 4 points already. So A will rotate around there, B will rotate around there, and C will rotate around there, and D will rotate around there. Sorry, this is D. All right. Now we are getting our moment of inertia. For A, we have mass 3, and the distance, we already got the distance earlier from this one, from the radius R. Okay, if you will still remember, so I will put that here again. Here also. So you have your distance R. Anong dili naman siya? Okay. The distance are for all the points. All right. So our distance r was 0.35 squared. Again, please do not round off yet. So 0.35 squared plus 3 times 0.35. They have the same distances, and finally plus 0.35 squared. So our moment of inertia is 1.5 kilogram meter squared for letter C if we are rotating at the center. All right. So now if we are going to determine which axis of rotation can we rotate our square the easiest, we have to find the moment of inertia that has the least magnitude. Okay, so here for A, it is 0.75, for B, 1.5, and for C, 1.5. Therefore, it is easiest to rotate at axis, what was the axis? At axis BC. Okay, because it only has 0.75 kilogram meter squared moment of inertia. Okay, so that means it is easiest to rotate around this point than this point and then that at the center. Okay, because at B and C, it is 1.5 kilogram meters squared. So it has greater resistance to rotate. Okay, so I hope you understand that one. All right, so moving on. I will share my screen again. Maybe we are over time. Okay, so it's there. Moving on to our topic. In your module, the rotational inertia or moment of inertia for various rigid bodies are derived there. Okay, so I give you here the summary. All the formulas already, it has already been computed and studied by the scientists. Okay, so you have there the formulas, and in your module, it is there being derived. Okay, so again, don't get intimidated with all the letters and the formulas. We also have the rotational kinetic energy, which is 1 half I omega squared. Okay, so for kinetic energy, we have 1 half mv squared, right? If you can still recall. Okay, so for rotational, instead of mass, we use the moment of inertia, and instead of velocity, we use the angular velocity. Okay, so you can determine which of the two you can rotate easily if the masses are here at the center or if the masses are there at the end. So, okay, so you have an example for that in your module that you can solve. So just take note of the example that we had earlier, and you can solve this problem in your module. Okay, so we also have the parallel axis theorem, which is the moment of inertia is equal to ICM plus MD squared. This, you also have an example for this in your module. All right, and so on. These are just derivations. Again, do not get intimidated with the formulas here. They are just simply derivations on how to get our moment of inertia for the various rigid bodies. Okay, so let's have our three more examples and we're done for this topic. Okay, first example, okay, kindly again um, take photo or screenshot so you can glance later. For the first example, a solid uniform sphere of radius r and mass m has a rotational inertia about a diameter that is given by 2/5 mr squared. A light string of length 3r is attached to the surface and used to suspend the sphere from the ceiling. Its rotational inertia about the point of attachment at the ceiling is, you have your choices. Okay, so stop share again and share this one again. Okay, so I hope you guys are still following. Click the subscribe button at the meantime. Okay, it's there. All right, so what was our problem? You have a solid uniform sphere. So according to the problem, you have a sphere and your sphere has a moment of inertia 2/5 mr squared. Okay, so that is already derived. Okay, now you have a light string. You use a light string to suspend the sphere on the ceiling. All right, and the length of the sphere, the length of the string rather, is 3r. Okay, now you are asked what will be the moment of inertia about the point of attachment at the ceiling. Okay, so you are asked for the moment of inertia if we are going to rotate here. We are going to rotate both the string as well as the sphere. So let's have that as our red. That means that is where our what that is the point where we are going to rotate. So which rotates there? The sphere will rotate there. The string will also rotate there. So there are two objects that are rotating in that point of rotation or pivot point. Okay, so with that, we can compute for the string first, the moment of inertia for the string. Again, our formula mr1 squared. Okay, so our mass of the string, we use m, okay, capital letter M, and our radius will be 3r, and that is squared. Okay, so our spring will be 3 times 3, wait, 3 times 3, that is 9. So we have 9 mr squared. That is for the string. Okay, and since we have our moment of inertia for the solid sphere, we have our string, we just get the total of that, or the sum. So you have for the string, which is 9 mr squared, plus our sphere 2/5 mr squared, that would be 9 and 2/5 mr squared. And 9 and 2/5 is equal to 47/5 mr squared. So that is our answer for our first problem. Okay, this should be squared there. All right, and for our problem number 2, I will share again my screen for problem number 2. Okay, problem number 2. Three identical balls with masses m, 2m, and 3m are fastened to a massless rod of length L. Okay, again, this is a massless rod, so we do not account for the mass of the rod. You are asked for the rotational inertia about the left end of the rod, so we are going to rotate it here. All right, so sharing to you my other screen again. All right, checking if it's there. Okay, let's have another page for that one. So you have your three masses. Okay, one, two, three. This is M. This is 2M. Sorry, it is not drawn to scale. This is 3M. Okay, and the length of the rod is L, and this is 2L. Oh no, sorry, L over 2 rather. This is L over 2, and of course another L over 2. All right, so where are we rotating? We are rotating at the left. So what are the points that are rotating there? We rotate our mass 2m. We also rotate our mass m. So getting the moment of inertia, our moment of inertia would be, first, we have our 2m. 2m times L over 2 squared plus our m, this one, m times L squared. So that will be the distance. M is here, okay? So the distance from M to our pivot point is L. All right. Now, computing 2M is equal to L squared over 4 plus ML squared. ML, this is not the Mobile Legends. 2 over 4 is actually 1/2 plus 1. 1/2 plus 1 is 3/2. So we have 3/2 ml squared. Hope you don't get confused with that. It's just adding fractions. And our last problem. Okay, sharing to you another screen. All right, our last problem, it says, what is the rotational inertia of a thin cylindrical shell of mass m, radius r, and length L about its central axis x prime? Okay, so get a screenshot again. I will be sharing my notes again. Alrighty, it is there. Is it there? All right, it's there. Okay, so you are given a cylinder with length L, and this is, I will use red for the axis of rotation. This is our axis of rotation, x prime, okay? And our radius is this, between the axis of rotation and the side of our cylinder. we are going to ask what will be the moment of inertia. Okay, so I again is equal to mr squared. So our mass, it is given capital letter M, and our R is also given capital letter R squared. So that's just it. That is our moment of inertia. So as what I've said earlier, do not get intimidated with the formulas, with the drawings and with the letters all over the place. Do not get intimidated because it's just easy. Just follow the formula for moment of inertia. I is equal to mass times the radius or the distance between the point and the axis of rotation. All right, so thank you for watching this video. And if you have questions with regards to the problems that you have or the activities that you have in your module, you can message me on Canvas. And for further assistance, come to discussion hour. So I hope you are doing your module, reading your module, and working on your module before discussion hour of every week. Okay, so that during discussion hour, you can throw me all your questions and for further clarifications also. So again, for module 4, do not get intimidated with all the formulas and the letters and the derivations. Okay, so it is just very easy. Just base all your solutions from the sample problems I had given you in this recording. So thank you very much for watching. See you again for our next lecture. Goodbye.